Hey guys, welcome to the lesson on bisectors of triangles. We start with a quick do now. Part 1 says write one property of perpendicular bisector theorem. Part B says to write one property of angle bisector theorem. So the property that I was looking for the perpendicular bisector theorem is pretty much stating that whenever we have two segments bisecting each other, or a perpendicular bisector, we know that no matter what point we choose for C on the actual bisecting segments, we can state that AC will be congruent to BC. And for the angle bisector theorem, we know that the distance, or the shortest distance from a point on your bisector to a point on your side of your angle should be congruent on both sides, like that. Which means I want to state that BD is congruent to CD. So these are just outcomes from the actual theorems themselves. We proved this back in lesson 3, I believe. Lesson 3. All right. So the title of this lesson is Bisectors of Triangles. We have our objective. Given an understanding of perpendicular bisectors and angle bisectors, students will analyze the properties that arise from bisecting triangles. So to fill in these blanks, we have students will use perpendicular bisector and angle bisector on triangles to analyze properties. We have a little bit of vocab for you guys. We have concurrent. These are, this is 3 or more lines that intersect at one point. So here's an example of that. We also have a circumcenter. The circumcenter is the point of concurrency of the 3 perpendicular bisectors of a triangle. So no matter what triangle, another example, no matter what triangle I draw, if I find out my perpendicular bisectors of each side of my triangle, so let's say this would be the half. If I perpendicular bisect that, I have my right angle. If I perpendicular bisect over here, here's my right angle. And if I perpendicular bisect here, there would be my right angle. They would all meet at one point. That point would be the circumcenter. And the last one is the incenter, the point of concurrency of 3 angle bisectors of a triangle. So if we have a triangle, we have this triangle up here. If I were to bisect this angle, meaning I would cut it in half, that would be my bisector here. This would be congruent to this. My bisector of my top would be there, meaning this would be congruent to this. And my last bisector is there, meaning this would be congruent to this. They would all cross at that point. That point would be called the incenter. So we had a construction in class where we worked with patty paper, and we were able to actually bisect a triangle, or perpendicular bisect each side of a triangle to create the incenter, which is located right here. So those are the kind of step-by-steps. You guys are more than welcome to pause now and try this out on your own. So I want to explore the circumcenter. I posted up a link on my file cabinet or my website for you guys to try things out. I'm going to go ahead and show you guys what that circumcenter would look like on the link itself. So this is what we would see. Again, I can drag any one of these vertices, and let's see what happens with this triangle. So notice it stays for the most part inside. The circumcenter is, again, it's where all these lines, all the perpendicular bisectors of each side of the triangles intersect. But notice if I make this a little bit smaller, I can have it on the line, or if I keep going, my circumcenter can be out of the triangle. So we notice 3 different properties when we create the circumcenter. So to go back, it states right one true statement about the circumcenters. Those were the properties I was looking for. So here we sum them all up. A circumcenter can be inside the triangle, on the triangle, or outside the triangle. And here we have each one of those pictures depicting each scenario. All right, so now we're going to move on to proving a circumcenter. So what we want to show based on this theorem, on this proof, I'm sorry, is we have given that PD, PE, and PF are perpendicular bisectors. So here we have our perpendicular bisectors. This one will be in blue. So with this one, and so with this one. So that's given information. We want to show that PA is equal to PB, which is equal to PC. So this would be PA, PB, and PC. To show that congruency, we're going to go step by step with our proof. So again, I'm just going to say what is given to us. We know that they're all perpendicular bisectors. So I'm going to go ahead and draw out what that means on my picture, then write it in words. A good strategy is always visualize what you got to write and then write it down. So I'm going to go ahead and label the congruencies. If it's a perpendicular bisector, we know that BD should be congruent to AD. We know that BE should be congruent to CE. And we know that AF is congruent to CF. These are all congruencies. So that's just given information. Now you can choose to write that in one or just leave it as is. Totally up to you. So we're going to go with the second statement now. The second statement states that PA is congruent to PB. So let's look at PA. PA is here and PB is here. If I were to isolate this triangle, or if I were to redraw this triangle, here it is. I'm going to go ahead and label it. It has my perpendicular bisector. It has my right angle. I'm going to label it A, D, B, and this would be P. So again, I just isolated this triangle here. So I'm making a comparison between PA and PB. Well, I also know that these things are perpendicular. And if we go all the way back to our first slide where we defined, there he goes, where we defined properties of the perpendicular bisector, one of the major properties was that AC was congruent to BC, meaning the sides of my triangles were meant to be congruent. So we're going to use this property in our proof. If we look here, we have that PB, or our side of our triangle, is congruent to, BP, our side of our triangle is congruent to PA. These are both of our sides. So by the perpendicular bisector theorem, we know for a fact that these two have to be congruent. So if we look up here, these two have to be congruent. I'm going to go ahead and color code that with blue, just to kind of throw it off. So this side has to be congruent to this side. And again, that's by the perpendicular bisector theorem. So we're going to write that statement in. Perpendicular bisector theorem. Now let's look at step 3. Our statement 3 says that PB is congruent to PC. And again, if we look at, or we would isolate this triangle, we notice that there's a perpendicular triangle, perpendicular bisector triangle, just like the first one. So this one would also be by the perpendicular bisector theorem. We finally conclude our last thing. If we visually see our picture up here, we notice that all of these three blue tick marks, or congruent marks, have been indicated to be congruent on the segments PA, PB, and PC. That is exactly what we needed to prove here. So if we have that down, our last statement would just be by the definition of equality. You can say that would be one way to conclude it. So just using this information here, it's PA is equal to PB, which is PB is equal to PC. So you can say definition of equality. Not so much a transitive property, but yeah. So we're just stating that they're equal, and that would be the proof. Now what we just showed is that all of these red sides are congruent to each other. This was something, this was a great idea that somebody said, hey, we should make a theorem out of this. So then we have the Circumcenter Theorem. All this states is The perpendicular bisector of a triangle intersects at a point that is equidistant from the vertices of the triangle, meaning if we ever have PD, so if we ever have PD, PE, and PF as perpendicular bisectors of a triangle, then by this theorem, but we just showed PA has to be congruent to PB, which has to be congruent to PC. So that's all for this theorem. Now, something we find unique about this is that if we were to take, for example, this center mark and maybe relate this to a circle, this becomes a radius of a circle. We can actually circumscribe a circle around my entire triangle. Now, what that means, better yet, let me just show you guys. So here we have my triangle, and here we have a compass. I'm going to go ahead and align it again at the center. I'm going to try to figure out the correct size to this vertice, and I'm going to use that kind of as my radius. So this becomes the radius of my circle. So if I were to continue drawing a line, there it is, I actually circumscribed a triangle in a circle. So I used the notion of this being my radius to create a circle. So notice it's equidistance here, it's the same distance here, and it's finally the same distance here. So we have a new vocab term as well. It means circumscribe. The circumcenter of ABC is the center of circumscribed circle. A circle that contains all the vertices of a polygon is circumscribed about a polygon. So here is our definition. That is what is meant to be circumscribed. Circle meaning around, and scribe meaning to write. We have our first example. Using the properties of perpendicular bisectors. So here we have this triangle. We want to go ahead, or we know that KZ, so here's KZ, LZ, LZ, and MZ are all perpendicular bisectors. So I'm going to write those in blue. Here it is, and here it is. Those are all in blue. We need to show or find HZ. So HZ would be this side right there. So if we were to isolate this triangle, so here you go. If I were to isolate this triangle, I'm going to trace over HZ, trace over this side. We notice we have this whole perpendicular bisector thing going on again. Meaning if I know this side, I have to know this side. So HZ is just using the property of perpendicular bisector is just equal to 19.9. And that's it. Here we have a few more of these examples using the exact same triangle. I'm going to run through these fairly quickly. So if we want GM, this one here, if we isolate this triangle, we can also apply a perpendicular bisector. We know that this side has to be congruent to this side. So for GM, our measurement is 14.5. For JK, or I'm sorry, GK, erase this, our GK triangle, GK, there's GK. Again, if I were to isolate it, I would be dealing with this triangle, and only that triangle. I want GK. If I know this side, I have to know this side. So GK would only be, or would be 18.6. Whoa, 18.6. The last one I want to find out, or the last segment, would be JZ, not the rap star, but the segment JZ. So here JZ is not, oh wait, there's JZ. JZ is right here. Again, we know that all of these are going to be the sides of our triangles, or our perpendicular triangles. So we know, if we know one of them, then we know all three of them. So if I know that all three are congruent, well, I know GZ over here is 19.9. That means JZ has to be 19.9. And we're done. So now we're going to explore the concept of in-center. First, we explored the concept of circumcenter. Now we're going to look at it in center. In center, again, just to recap, is the point of concurrency of the three angle bisectors of a triangle. So to kind of just draw a picture, roughly, is if I have a triangle, any kind of triangle, I can bisect one side of it, there's my bisector, bisect the other side of it, and then bisect the top. Where they all meet is where the inner center is, or the in-center is. There it is. So let's explore these properties and see if we can write one true statement about an in-center. So here we have our triangle. Again, I'm able to move these vertices anywhere I want. So let's kind of play around with vertices C or angle C and see what we notice. Notice before we even started, each side has congruent angles because it's a perpendicular. I'm sorry, it's a angle bisector. So I'm going to try to push the in-center as far out as I possibly can. Notice that it doesn't go. It doesn't go outside. We can never have the in-center outside of our triangle or make it equal to a line or to one of the sides of it, no matter what we do. So that becomes a good rule for us to write down or to note. So using this, we can conclude that, yeah, no matter where we put the triangle or where we put the in-circle, it always stays inside. No matter if the triangle is acute, obtuse, or right, it always stays inside. So that's one of the properties of the in-center. Hence the word in, meaning always inside. The circumcenter never has the word in on it, so it can float outside or it can be on a line. So let's look at this proof. It's very similar to the one we had before. Here the given information is that AP, BP, and CP are angle bisectors. So we have AP, it's bisecting, BP, it's bisecting, and PC is bisecting. We want to show that PD, PE, and PF are all congruent statements. So let's look at the first one. Again, we can just write our given information. I like to draw onto my pictures itself, so we know that this angle is congruent to this angle. I know that this angle is congruent to this angle, and I know that this angle is congruent to this angle, because those are all bisectors. You can write that information there, you can just leave this and then given. So let me jump into the second one. If I know this angle, which I mean I do know it, let me trace it over and see if I can make a better picture of it. Here is angle, oh, that's pretty bad. Let me try that again. Well, okay. Well, it just keeps showing up. I guess it doesn't want to go away. All right. Well, we have that angle. I'm going to go ahead and draw this angle out. Here's one. Here's my first angle. Oops. Sorry. All right. If I were to bisect this angle, so it's this red one right there, and I follow it all the way through, I know that these two are congruent. Well, then I know that I can create, or one of my properties that we stated in the beginning was this point on my bisector. I know that the distance between a side or both sides of my triangle and a point on my bisector has to be equidistant. So that's this distance right here and this distance right there, indicated by this right angle. That is the shortest distance. So I also stated that they should be congruent. So that's why PF and PD are congruent. And this, or this reason, would be because of my because of my angle bisector theorem. So this one would be angle bisector theorem. So let me clear this up. Okay. Very similarly, we have PD. So PD is congruent to PE because, again, if I were to stretch this angle out, and I would bisect the angle, which is this one here, I create these two lines that are congruent. They have to be congruent by the perpendicular bisector theorem. So I can write that for number 3 as well. I mean, angle bisector theorem. And the last one is just showing PD is congruent to PE, which is congruent to PF. Again, this would just be by definition of equality, or I would use definition of equality. And we're done. So we've literally now showed that whenever we have angle bisectors, wherever all my angle bisectors cross, we create an incenter. Or we state furthermore that whenever we have an incenter, then the sides, or PD, PE, and PF have to be congruent. If we relate this again to circles, we know that all of these three sides that are congruent should be the radius of a circle. So we're going to take a look at circles again. That was circumscribe. Now we're going to look at inscribe. So if I place my needle at the center and I measure one of these sides with my compass, I can go ahead and draw around, creating a circle inside, hence the name inside my triangle. This is known as an inscribed circle. So again, my needle at the point, all these sides should be the same. Well, it makes absolute sense because radius or radii will always be equal inside a circle. So that is an example of our inscribed circle. Well, here's the definition. A circle inscribed in a polygon intersects each line that contains a side of the polygon at exactly one point. That point would be your incenter. Okay, let's look at an example of this. Here we have JV and KV are angle bisectors of J, or my triangle JKL. So JKL. It says find each measurement. So I want to find the distance from V to K. So the distance from V to segment KL. The shortest distance here would have to be, boom, a right angle. Let me try that again. It would be a little bit more like this. So it has to be a right angle. Moreover, if we know that they're bisectors, I know that this is congruent to this. So yeah, this is a bisector. So by the angle bisector theorem, if I know that WV is 7.3, then the distance between then the distance of V to KL, this has to be 7.3 as well. The last thing we want to find out is angle VKL. So here's V, here's K, and then here's L. Again, I stated because they're bisectors, these have to be congruent. So if I know this angle, I know that that's also congruent to this angle, which is also congruent to this angle. So measure angle VKL is equal to 19 degrees. And we're done. Well, actually, let me make a quick correction there. Because we can't assume that these two are the same. So if I know that this angle is 19, then I do know that this angle is 19. So this complete angle itself should be 38 degrees. And I know that this angle is 106. So if I add 38 to 106, I should have that these two angles together are 144. And I want to find out this missing angle here. So if I do 144, or better yet, if I do 180, minus 144, I end up obtaining 36 degrees. So this angle up here, its complete angle is 36 degrees. Since we bisected that angle, half of that angle would give me 18 degrees. So the measure, I was off. The measure should be 18 degrees. So it would be half of this one, 18 degrees. And then we ended up with an exit slip in our class. Alright guys, so that's it for this lesson on bisectors of triangles. I hope it helped. Please pause and resume as you feel comfortable, and I hope this helped. Bye.